So welcome to the second part of the video lecture series on Introduction to Computer Networks on the topic of transport and application layer. So we'll jump to the point where we left off, which is right here. All right. So we have been talking about what the transport layer does for us, that is, manage ports and allows us to have multiple applications running on a single host to communicate over the network, right? So these applications in the transport layer can use, most commonly, two of these protocols. The first one would be the UDP, or the User Datagram Protocol. The second one is TCP, or the Transmission Control Protocol. Uh, to summarize it very fast, the UDP protocol is unreliable but fast. On the other hand, the TCP protocol is reliable but slow. And we'll look at the reason why these two protocols have these specific properties, and also when would each of these would be suitable. However, both of these protocols are running in the transport layer. So the UDP protocol provides unreliable communication, and the overall concept is that the delivery of the messages, the delivery of the units of data between two hosts, when performed through UDP, is not guaranteed. And the reason is because the ports are dynamically allocated and the source and destination are not communicating with each other with respect to which packets have been received, and which segments have been received, which segments have been dropped or lost in the process of transmission. So the source port is filled in by the operating system as the message is being sent, and when it reaches the destination port is allocated by the operating system on the destination host, and it goes into a queue from where it is distributed into the specific application. The reason why we call it connectionless is because there is not a preset connection between the source and the destination that is set up before the packet is being sent. It is very dynamic and ad hoc, and there is no information regarding the transmission that is occurring between the source and the destination. It wants the packet to be delivered as fast as possible to the destination, and the segments which are created in the process, some of them may be lost, some of them may be dropped, some of them may be discarded, but regardless, the transmission will continue. The delivery is where the multiplexing comes into play more, and it's actually rather easier to understand. So let's say we have the operating system boundary here. So the kernel refers to the core of any operating system. So this is where the boundary is for the operating system, and we have a bunch of applications which are running on top of an operating system. And the operating system is responsible to manage each of these ports. So these are the queues which are applied for each port that is allocated by the operating system. So when a packet arrives into the host from the network, it goes through the interface, goes through the link layer, the network layer, and the packets that come into the transport layer. And the transport layer first tries to identify each of the segments and then places them accordingly into whichever port the destination is specifying. And that is why the overall process, we can consider this to be very fast, and there is no confirmation that the receiver sends back to the sender that I have received this specific segment, so I'm missing one of the previous ones whatsoever. So nothing of that sort occurs during the delivery of the UDP segments, and it is just placed in the queue, so the applications here can continue its operation without being held up. So the datagram for UDP looks like this. It has 16 bytes for the source port. It has another 16 bytes for the destination port. Then we have something that we call the checksum. We'll look at it in a short while. And then we also have a field that we call the length. That means it is implying the length of the data field that we have coming next. So whenever a UDP datagram is received, the operating system will check the source port, and then it will check the destination port to identify where it should be forwarding it to. It verifies the checksum, which guarantees the integrity of this datagram to make sure that there are no errors inside it, and then obtains the length to tell the application that you have this much of data coming in your way. So let's look at what the checksum does for us. So this is a form of protection against errors. So this is more like error identification, and what it is meant to do is to be able to identify if any of the bits or any of the information within the packet got modified in the process of being transferred from the source to the destination. And it covers the data which is within the datagram. It includes the UDP header, that is the source, the destination, and something that we call the IP pseudo header. So one thing to note here is that IP is a part of the network layer. So how does the transport layer know about it, or what are we referring to the pseudo header? So that is why we call it a pseudo header. That is, it is a part of the header that is from the network layer, but the datagram checksum includes the IP address fields from the network layer while calculating the checksum in the transport layer. And the way it works is like a mathematical function. So you have, let's say, field 1, then you have field 2, field 3. So whatever that you would want to include as the information, you take it in all together, and then you pass it through a mathematical function. So once it passes through the mathematical function, as an output, it gives us a value which we can say is the checksum. So what happens is the source, when it is sending out a specific segment, it takes all of the required fields in the datagram, performs the mathematical function, and then calculates the checksum. And then it actually puts it inside the datagram. At the receiver's end, which is the destination, the host takes in the datagram, picks out the checksum, and also takes out all the other fields which are there, puts them together, and then performs the mathematical function to calculate the checksum. So now this is the new checksum which the destination just calculated, and this is the old checksum it received in the datagram, and the destination will then use the one that it received and the one that it calculated and compares it. And the idea is that if these two are equal, that means the datagram which was sent from the source has not been modified in any form when the destination received this datagram. If the comparison results and shows that they are not equal, that means the datagram has been modified while it was being transferred from the source to the destination. And the fields which are included while calculating the checksum, it covers the data, the UDP header, and the IP pseudo header, which we have already explained, that is the IP addresses and some relevant information from the network layer. So given that UDP is fast but unreliable, we can classify the specific type of applications which are suitable for UDP. One of the best examples that you can have are audio and video streaming. Let's say you are making a call over WhatsApp, or you're watching a video on YouTube, and we know that sometimes we see a crack in the voice when we're talking over with WhatsApp, or when we're playing a YouTube video. Sometimes the video stream kind of flickers a little bit. It could be using IPTV, any form of VoIP services, and all of these services and applications are examples of cases where we, as a user, would expect the time and the smoothness of experience to be more of the primary concern. Even if the voice cracks a little bit while I'm talking to someone, I would still want the latency to be very low. So that is my primary objective as a user and my experience when using this application. So, as a general rule, applications which require very low latency and basically can tolerate some loss of data during the transmission, with the objective that the user should be provided a smooth experience and the continuity of service, would be suitable for UDP. So now let's look at TCP, which is the Transmission Control Protocol. So the Transmission Control Protocol ensures reliable communication between application processes. And this guarantee of delivery is ensured by something that we call the sliding window protocol. So this is an additional concept which runs within the TCP, and basically it tells or communicates with the destination or the receiver that I'm going to send, for example, 5 segments right now. Let me know if you have that much space in your buffer. If there isn't, then I will shrink my window. If you have a lot of buffer present, a lot of space left in your buffer, then I will increase the size of my window. And this agreement between the source and the destination results in efficient transfer of data between the source and the destination, and also make sure that they are in sync. So given that TCP allows this reliability and control of the application, we say that TCP is connection oriented. That means there is a conversation between the two endpoints, the source and the destination, before the actual transmission starts, and also at the end of the transmission, to ensure that everything that is intended to be transferred has been successfully and completely transferred. TCP also allows what we call flow control and congestion control. So flow control refers to the fact that it prevents the sender to continuously keep on sending packets in case the destination is overwhelmed with a lot of incoming packets, not only from this one single sender, but from multiple other senders. Basically, if the buffers at the receiver's end, if they are getting filled up, then the sender needs to slow down. That is what we call flow control. And the other thing is what we say as congestion control, which means that based on the transmission delay between the source and the destination, and also if there are packets which have not arrived at the destination, although they have been sent out from the source understands that the network has been currently overloaded, and there are a lot of other packets which are running through the network. So this is what we say congestion control from the sender's end, so that the sender, the receiver, could be guaranteed that the complete data is transferred between these two endpoints. So the concept of TCP delivery is almost similar to UDP, just the fact that the buffers of the application center and the receiver application, they are in sync in the sense that they are aware of each other's capabilities and how much the network can support in terms of the transmission load. And this control is what we call as flow control and congestion control with TCP. And given that TCP is a little bit more complex than UDP, you can actually take a look at the structure of the datagram between these two, and you will see the number of fields that we have in a TCP datagram is much more compared to the UDP. So in the UDP datagram, we have the source port, the destination port, the length, the checksum, and then we have basically the data. And in the TCP datagram, we have the source and destination ports. This is required by the transport layer. Then we have something that we call a sequence number, which actually implies to the number of that specific segment which is being transferred. Also, we have an acknowledgement number, which implies the specific segment which has been received by the destination. And then we have some additional fields such as flags, window size. This is the size of the sliding window. Checksum, which is the same as in UDP. Urgent pointer. This kind of prioritizes different packets as it goes through the network. And some additional fields which are optional.